Good evening, ma'am.
Good evening.
We will start in next 2 or 3 minutes, ma'am.
It's okay. लास्ट डे आज
Yes, ma'am. आज last day है. Yeah.
आपका भी बिजी चल रहा होगा
Yes, ma'am. काफी यही चल रहा है.
तो अभी घर जाना होगा दिवाली पे
Yes, ma'am. अभी दिवाली पे घर आना है मेरठ, देन फिर यहाँ से रिजाइन करना है एक्चुअली.
कहाँ जा रहे हो
यूनिवर्सिटी ऑफ वेस्ट इंडीज, मैम.
वेस्ट इंडीज में जा रहे हो
Yes, ma'am.
ओके गुड चलो कंग्रेचुलेशंस
Thank you, मैम.
कब जा रहे हो
जनवरी ज्वाइन करना है, मैम.
ओके तो वहाँ क्या परमानेंट है या टाइम बाउंड
नहीं, परमानेंट है, मैम.
चलो गुड
थैंक यू, मैम.
आप लोग यंग हो कहीं भी जा सकते हो
Yes, sir.
अब हम लोग तो ये अभी बस यहीं से कुछ करते रहे अब
That will be nice for us. I'm very honored कि आपने accept किया. That is very honored for me. Rahul, I think we can start so people can join later.
या अभी 15 हैं
Yeah.
13 ही लोग हुए
They can join later.
इट्स ओके
Good evening, everyone. I am Rahul Samuel Norona on behalf of the Department of Statistics and Data Science at Christ Deemed to be University, Bangalore Yashwanthpur campus. I extend a very warm welcome to all the participants, resource persons, and esteemed guests joining us today for this national level faculty development program on advanced statistical techniques for academic excellence in data analytics of stochastic processes. And to lead this session, we have amidst us Prof. Kanchan K. Jain. I take this opportunity to introduce Dr. Professor Kanchan K. Jain to all of you all. Professor Kanchan Jain is a distinguished professor at Punjab University's Department of Statistics, Chandigarh. She specializes in reliability theory, survival analysis, measurement error models, actuarial statistics, income inequality, and biostatistics. With a career spanning more than 43 years, Professor Jain has contributed significantly to her field, publishing more than 70 research articles in reputable journals and presenting papers at various conferences. Her academic work also includes authoring a book chapter and serving as active members of different professional statistical societies. Professor Jain is a life member at International Indian Statistical Association and Indian Society of Probability and Statistics, and member at Institute of Actuaries of India and Institute of Actuaries, London. The Statistical Society of London. Additionally, she has supervised multiple doctoral theses, guiding future researchers in statistical methodologies. Professor Jain's expertise spans interdisciplinary. So, without further ado, I hand over today's session on stochastic processes to Professor Kanchan K. Jain. Over to you, ma'am.
Thank you, Mr. Samuel, for nice introduction. Let me present my Can you see my screen?
Not yet, ma'am. I think not
Not
yet.
yet. ये क्यों हो? But क्या हो गया? But I shared it.
Ma'am, stop it and try again.
Yeah, I'm doing that. So I'm sharing my screen actually.
Okay.
It's standard or voice isolation. I think that's fine.
Yeah, ma'am, it is visible.
It's visible.
Yes, ma'am.
It's okay now, Dr. Shikhar?
Ma'am, it is okay, ma'am.
Okay. So good evening, everyone. I shall be talking on stochastic processes. I'll try to cover as much as possible, though 2 hours is not a very long period to do justice to the subject. But still, I'll try my best to give you an insight into this topic. So I'm no longer with department. I have retired from there last month. So I am now working as a freelancer. And I had spent 44 years in the Department of Statistics, Punjab University. So I have not joined any institute, but I'll try to be active. So first of all, we wish to define what is a stochastic process. Everyone is aware of the concept of random variable. When we consider a collection of random variables or a family written as x of t, where t belongs to capital T, this capital T is the set over which your t is taking values, and this is known as the time space. Now, time space can be discrete or continuous. Discrete can be 0, 1, 2, n, like you have some specified values, or it can go to infinity. And for the continuous case, you have intervals 0 to infinity or minus infinity to infinity or AB. The state space of a stochastic process, which actually we denote by capital S as sample space in probability theory. Here, this is state space, but it is now set of all the values or realizations of xt on capital T. If my t is 0, what is my x is 0? That value, then x of 1, x of 2, and so on. That will be forming our state space. And this can also be either discrete or continuous. Now, types of stochastic processes, when we have time and state space, we can have combinations, both discrete, one discrete, other continuous, or both continuous. First, I'm taking up the example of both time and state space being discrete. First example is, suppose you are rolling a die 40 times. We know that die has 6 faces. So state space will be taking values 1 to 6. And the time space here, because I'm rolling it 40 times, it will be 1 to 40. If I change this to 30, this will be 30. And one possibility is, this is not the only possibility, x of 1 can be 4. It can be any of these 6 values. So suppose x1 is 4, x2 is 5, x3 is 2, like that, and x40 is 5. So these are the realizations. These are values of small t, 1 to 40, and 4, 5, 1, 2, 3, 6, they are the realizations. Second example is, suppose xn denotes the number of accidents on nth day of a month. Now, maybe there is no accident. Realization will be 0. One accident, 1, then 2, and so on, because I don't know how many accidents are going to happen. And t, it depends upon which month are you considering. So t can be 1 to 30, or 1 to 31, or 1 to 28, or 1 to 29. So this is for a leap year. We are not specifying. So t could be any one of these 4 sets. The next is, we are taking discrete time and continuous state. You see, stochastic processes have many applications. In financial market also. So if we consider closing price of a company stock at the end of the nth day, S will be, I don't know what will be the closing price. There will be some range. And T, and then at the end of nth day, I'm saying. So it is 1, 2, 3. I could end it with 30, 31 like that, but I'm not doing that because I'm not saying which day. Then there can be more examples. Then continuous time, discrete state. We are now interchanging. What happens here is, suppose there is an insurance company who classifies the policy holders as healthy, that means H, sick or dead. So state space is H, S or D. This could be one of the possible states. And time space here will be starting from 0 till infinity. When we write this, this means we are studying this for a longer time. Then continuous state, continuous time, both are continuous. The best example for this is a Brownian motion. It's also known as a diffusion or Wiener process. Here, x of t denotes the position of the gas molecule at time t for gas in a container. There is gas in a container, the molecules are moving. So this is the position of the gas. They travel along a path and direction changes when they touch walls of the container. Here, T as well as they are continuous because we don't know what is going to be the position and what is going to be the time at which that particular position will be attained. As I said, there are many applications of stochastic processes. Stochastic processes are random processes where there is randomness, and in real life we can see this randomness around us in many cases. So first is population size at time t, content of water in a dam at time t, inventory with the manufacturing unit at time t. They are all changing. Number of persons waiting in a queue at time t. Then opening price of a stock on a particular day of the month. Number of packets waiting in buffer at 10th time unit in the communication routes. Number of customers in barber's shop after nth customer leaves. So there could be many more examples. Even queuing processes are examples of stochastic processes. So this fourth illustration is from queuing. Now there are two types of Markov stochastic processes. One is Markov process, the other will be Markov chain. What is a process? This is my stochastic process. You see, some books write X, S, comma T, where S belongs to capital S, T belongs to capital T. But in the beginning, they write that notation, but finally they come to this only for the sake of convenience. So this is a Markov process if Markovian property actually is lack of memory property type thing. So if the value of xs is given or known and values of xt where t is greater than this s do not depend on the values of xu where u is smaller than s. So that means if you know present, you don't need to look at the past, and the future will depend only on the present and not on the past. So this is Markovian property. And mathematically, this can be written as if I have these time points, which are ordered, T1 is the smallest, that means the earliest time point. And here I have T, which is the largest. So if we write the probability, the x of T lies between A and B, given x of t1 is x1, x of tn is xn, then this is same as probability of whatever we had here, but now we'll forget about the previous points and just depend this probability on the last point. Last means before t. Here I had tn less than t. So this is x of tn equal to xn. So this conditional probability is changing to this simplified form. So Markovian property helps a lot and it makes things simpler. Now what is a Markov chain? When we have discrete time space and discrete state space, then Markov process becomes a Markov chain, and which we abbreviate as MC. Here also, we are choosing some points. Xn equal to k means at the nth time point, state of the system is k. When I know x naught is the initial state, then we go on to x minus 2, then xn minus 1, and here I had xn equal to k. So, here again, I'll forget about everything here. So, if I just don't think about these, then Markovian property says my probability xn equal to k given all these is just the last point, n minus 1 equal to j. Now what is a transition probability? Transition probability it is the probability of change or movement from one state to another. Like you are standing at one place, you wish to move to another place, then to another place, then what are the probabilities? Because if you move from the initial position to the first step, you take one step, and that will be your one-step transition probability. So if I have these states, I and j, from S, the state space, Pij1. Pij means starting from I, going to j in one step. And this is for simplicity written as Pij. And this is you start from I at the nth step, and at the next step, you are at j. This n has no relevance actually here. I could have written x naught equal to I, x1 equal to j here. Only motive is that movement from I to j is in one step. It can be from 0 to 1, it can be from 1 to 2, like that. Then once we know what is a transition probability, this concept is a very important concept in stochastic processes. So let S be the state space. Transition probability matrix is written in this form. You see, I have 0, 1, 2, 3, so on states. 0, 1, 2, 3, so on states. Here, 0 to 0. We are moving from 0 to 0. So P0, 0. Then 0 to 1 is P0, 1. 1 to 0 is P10, P11, and so on. Here I will have P02, here I'll have P12, like so on. So we can have a finite number of states sorry, or an infinite number of states. Sum of each row here will be 1. This is the condition for a transition probability matrix. So sum Pij, when sum is taken over J, this should be 1 for ith row, and all are greater than or equal to 0 because they are probabilities. And this matrix is called a stochastic matrix because rows are adding up to 1. If all rows, they add up to 1 and all columns also add to 1, then TPM is a doubly stochastic matrix. Not all TPMs are doubly stochastic. They will be stochastic matrices, but they need not be doubly stochastic matrices. And if PII is 1, that is I to I is 1, that means I is an absorbing state. Because once you start from I, you are again in I with probability 1. So that is a sure event, and this is an absorbing state. So this is absorbing the process. The ith state is being absorbed. This example is again for a motor insurance company. No claim discount model, NCD model is the name of this model. There are 3 discount levels: 0, 30, 60. So state space is 0, 30, 60. It's given that probability of no claim is 3/4. Therefore, if I want to find probability of claim, this will be 1 minus probability of no claim, which will be 1/4. Another thing that we know is that all new insured persons, they are at 0% discount level. They start with 0. If there is no claim during a year, then they move up 1 level or remain at 60%. 60 is the maximum. So if they are already at 60 and they don't claim, still they will remain at 60. If 1 or more claims, then they move 1 level down or stay at 0, because from 0 they cannot move down. So they will stay at 0. So here, if we write the TPM, 0 to 0 means discount was 0 in the initially when the insurance was taken out, and after 1 year also it is 0. That means the person has claimed and probability of claim was 1/4. So first row 0, 0 is 1/4. 0 to 30, that means the insured has moved 1 step above, and that means he has not claimed. So 3/4 is the probability. Then 30 to 0. Now this is falling down from 30 to level 0. That means claim has been made. 30-30 is not possible because from 30 the person will either move to 60 or come down to 0. So this probability is 0. 30 to 60 means moving 1 level higher, So no claim, 3 by 4. Up 60 to 0, not possible. Those steps, दो levels down नहीं हो सकता. Then 60 to 30, one step down. That means claim has been made. And 60 to 60 means no claim has been made, which is 3 by 4. And we can see that this is a stochastic matrix because all row sums are 1. All 3 rows are adding up to 1 here. This was writing the TPM actually. There is a result which says the TPM together with initial distribution means distribution of x naught, completely specifies an MC. I have another example. Suppose A and B are 2 brands of coffee and a customer uses at least one of the 2 brands. This is given to me. X1 is 1. You see, I'm labeling 2 brands as 1 and 2. My state space is this. See. So X1 is 1. The first type of coffee. This probability is half and probability X2 is 1 is half. This is given from past history. If I write Xn as a brand bought by the customer at nth stage, I'm supposed to write the transition probability matrix. Actually, no, sorry, it's given to me again. This is my state 1, this is 2. And T, I'm saying at nth stage. So first stage, second stage, third stage, and so on. These are my probabilities. So P11, P12, P21, P22. Suppose I am interested in finding now X2 equal to 1 probability, this one. I'm given for X1 equal to 1. I wish to find this probability. That means at the second step, the person is using first brand. Here I am using theorem of total probability. So X2 equal to 1 given, X1 is 1 into probability X1 is 1 plus X2 is 1. This is fixed actually. I'm changing this X1 equal to 2 because there are only 2 possibilities into probability X1 equal to 2. Now from the matrix, this probability we can see is 1, 1. Both are 1. So 0.8. Probability X1 equal to 1 is given to be half. So half. Plus, this is 2, 1. 2, 1. So 2, 1 is 0.5. So half, or I could have written 0.5. Then probability X1 is 2. X1 is 1 is half, so probability X1 equal to 2 will be also half. 1 minus half. And when we solve it, it's 0.65. So 0.65 is the probability that at the second step, the person will be using first brand of coffee. And this probability X2 equal to 2 will be 1 minus this, which will be 0.35. So probability of using first brand is more than using second brand. Previously, I defined one step transition probability. Now this is n step. In n step, we are looking at the probability after a gap of n. So here I start with xm. Here I add n to m steps. So xn m plus x of n plus m is j, given this. So I to j in n steps. Some books write brackets around this n, some books don't write. I am not putting brackets around n. Then this is also a very important result regarding these more than one step transition probabilities. Chapman-Kolmogorov equations. We take this to be a Markov chain. Suppose you have two states in S, then Pij n plus m. That means you are starting from I, moving to j in n plus m steps. Now, when that is happening, that means there are intermediate states. You go from I to k in n steps, pk j to m in m steps, and this k belongs to S here. There may be two states, there may be three more states, so it will be summation of that. So actually what it is going via something. If I want to reach at some place, in 3 days, I can go from I to k in 1 day, then from k to j in 2 days. Or I can go from I to k in 2 days and k to j in 1 day. This means P of capital P was my transition probability matrix. Pn plus m. This means this is the product of p raised to power n, p raised to power n. This is my n plus mth step transition probability matrix. And this is written as the product of these two. So if I put n as 1, m as 1, it's p2, which is p star p, which is p square. Then p cube will be p into p square, which is p cube. So if I am interested in finding more than one step probabilities, either we can go through these equations or we can find out the multiplication of the matrices and then conclude about the probabilities. Suppose there are two states now. One is 0, no rain today. And one is rain today. So there will be a 2 by 2 matrix, 0 to 0, no rain today, no rain tomorrow. Here it is no rain today, but rain tomorrow. This will be rain today, rain tomorrow. This will be 1, 0. So rain today, no rain tomorrow. 0.4 will be the probability of no rain today and rain tomorrow. You can interpret them according to the way we write the states. My interest is in finding that I know rain today. What is the probability that rain after 3 days? This is x naught is 1, rain today means 1. So x naught is 1, and our interest is in finding after 3 days. So x3 equal to 1. Again 1. If I had no rain after 3 days, this will become x3 equal to 0. So what it is? It is 1 to 1 in 3 steps. That means your interest is in P113 according to the notation that we used for n-step transition probabilities. So we have now two options. Either find P cube and take this element from there, or you use the Chapman-Kolmogorov equations. What we are doing is, I have split here. Sorry, here I put the brackets, here I am not. This is by mistake. So 1 to 0, 0 to 1. Finally, you have to come to 1. So this has to be 1. Then P111, P112. And when I further split, because this has to be split again, this one, I know one-step transition probabilities. So this again is P10, because here initial state is 1, final is 0. So starting from 1, I have to reach 0. So this 2 is being split as 1 plus 1. Similarly, 1 to 0, 1, 1, here I had 0, it's 1 here. Plus, similarly, we go about this here. This 2 is split as 1 plus 1, 1 plus 1, and we are taking intermediate states. So after putting the values from this P now, P10 is 0.6, this one. This comes out to be 0.526. So either I could find P square here, multiplication, and then find P cube using P square. Or I can go through R. Let me go to R. I'll show you. You see this, you can see this R screen. Hello.
Yes, ma'am, we are able to see.
Okay. So we have to install the package matrix. After installation is complete, you know you have to call the library. Then we write the transition probability matrix. There were 4 entries, 0.3, 0.7, then 0.6, 0.4 in the second row. So this is matrix. By row is true because we have to put in 2 rows. Then I print P. Suppose I have already installed actually. So library matrix, now I print P. Here in the output window, you have this P. This is what we had there. Now P2 I find, actually it's P square, but I've written it as P2. So P percentage star percentage P. Here you are multiplying 2 matrices, not the elements. So this is your P2, P square, sorry. Then if I go to P3, now here I am using P2, P and P square. Then my print P3, this one. So if you look at this, I needed P113. So actually mera 0, 1 hai. Here it's showing 1, 2. But we'll go by our notations. So this is my priority, 0.526. So this is easier. And there's another method also. You raise P to the power. There's another command, which I will show you later. And so I'll skip this R code. This was my R output. So here, see, 0.526. So P113 is 0.526. And here we had found it to be 0.526. So we are getting the same answer. Once we have defined these transition probabilities, we come to communication. Communication in simple words is just talking to one another. If you want to talk to somebody but that person doesn't want to talk to you, that is one-way communication. But if you want to talk and the other person also wants to talk to you, that is two-way communication. So here, first is state J, is said to be accessible from state I if Pi from I to j in n steps is positive for some integer n greater than or equal to 0. This is accessibility. Here communication means two states communicate if I goes to j. I goes to j means this thing, and j goes to I, pji m for m greater than or equal to 0. Matlab both way accessibility is there. So this means I and j, they are communicating. We have arrow on both sides. If we have accessibility, then it is one-way arrow. And this concept of communication is an equivalence relation, which means I communicates with itself, which is reflexivity. If I communicates with j, then j communicates with I, which is symmetry. If I communicates with j, j communicates with k, then I and k communicate, which is transitivity. So these are the three things that are to be satisfied for any relationship to be an equivalence relation. This communication partitions our state space into classes which are known as communicating classes. You see, when you have a number of states, all states may not communicate. So we have different classes. Sometimes they communicate, sometimes they don't. So whichever are the communicating classes, we put them under one class. Now what is irreducibility? 1 and 2 communicate. This means they are in the same class. If 1 communicates with 2, 2 communicates with 4, this will mean by transitivity that 1 communicates with 4. So 1, 2 and 4 are in the same class. So an MC with all states communicating with each other is an irreducible Markov chain. You can't split it. So there is only one closed class. All the states fall into one class, and which is known as a closed class because it's not possible to come out of that. And if it is not irreducible, it is called reducible. Period of a state is d of I. This is the most commonly used notation. It is the greatest common divisor of all those integers n greater than or equal to 1 for which probability is positive. This means PII. If you have a state and it's possible to return to the same state in 1 steps or 2 steps or 3 steps, then D of I will be the greatest common divisor of those integers. If 2 states communicate, they should have the same period. We prove it theoretically while teaching stochastic, but here I don't have that much time. So I'm just mentioning the result. Converse need not be true. They can have the same period, but they don't communicate. If PIIN is 0, then D of I will be 0. If DI is 1, then state is known as an aperiodic state. Otherwise, it is a periodic state, but if period is 1, we call it a periodic state. And an absorbing state will always have period as 1, because it's not possible to come out of that state. So period of that state will be 1. Now this example finds the periods. We have this state space starting from 1 going till n. The TPM is 1 to 1, 0, 1 to 2, 1, 0, so on. In the second row, we have 2 zeros, 1 and zeros. Then in the last row, we have 1, 0, zeros. So all rows are adding up to 1 here. Here, if I start with 1, I can see 1 goes to 2. That is obvious. 2 goes to 3. 3 will go to 4. N will go to 1. N is again going to 1. So how many steps have been taken? Starting from 1, reaching 1. There are n steps. So period of D1 is n. Then if I start from 2, 2 goes to 3, 3 will go to 4, and so on. N will go to 1 and 1 goes to 2. So it's possible to reach from 2 to 2 in n steps, and period of 2 will be n. Similarly, for third one, same period, and so on. You see, I said in the previous slide that communicating states have same period. Are they communicating? 1 is going to 2. ठीक है, एक ही step में जा रहा है. 2 is going to 1 in n minus 1 steps, but it is going. So 1 and 2 are communicating. 2 goes to 3, 3 goes to 2. There is a path. The number of steps may be more, but there is a path. So 2 and 3 will communicate. Similarly, 3 and 4 will communicate. And if you go on, you will be able to see that all states are communicating with each other. And hence, period of each state here will be n, and this Markov chain is also irreducible. Because when all the states are communicating, you have only one closed class. So this is an irreducible Markov chain. You see, earlier we defined transition probabilities. This is first time or passage probability. First word is important here. What is happening? You start from I, then you look at first return to I. It's not return to I. So first return will be at nth step or transition. So instead of P, now we are using the notation F. Start with I, reach finally I at nth step, but in between I is not attained. So that's why it makes this the first return. Matlab you will not be able to go to I at x1, x2, xn minus 1. Fii0 is 0 for every I. Pii0 will be 1. And this is the relationship between these two. This is n-step transition probability and this is first time or passage probability. This was from I to I. If you take start from I, first time J is attained. So now we are at J, starting from I. So J should not be attained in between. So we have xk not equal to J for k equal to 1 to n minus 1. And again Fij0 will be 0. Then we study the recurrence transience of the states. Suppose we write Fii as the sum of first passage probabilities. And Fij is the sum of Fijn's. Fii0 is 0, so we start n from 1. And state I is a recurrent state if Fii is 1. And if Fii is less than 1, then I is a transient state. It's not a recurrent state. Then if a state is recurrent, we have to check whether it is positive recurrent or null recurrent. So if I take Ni as the number of steps which are required for first return to I, knowing that start point is I. First passage probability means the number of steps required will be small n, where n can be 0, 1, 2, so on. If I take this capital Ni is a random variable. So we can write expected number of steps, which is expectation of Ni. And using the definition of expectation, we can write it as n Fin, and the notation is mu I. This is called mean recurrence time. So if we find mean recurrence time and it comes out to be finite, then our I will be positive or non-null recurrent. And if it is infinity, then I is a null recurrent state. If a state is positive recurrent and also aperiodic means its period is 1, then it is known as ergodic state. So ergodicity means positive recurrence and aperiodicity. Now these concepts of positive and null recurrence, they are class properties. This means if a Markov chain is irreducible and a state is positive recurrent, then all states will be positive recurrent. But if all communicate, then once we find one of them is positive recurrent, we can immediately conclude that others will also be positive recurrent. And any absorbing state will always be recurrent. Because once it is in there, it cannot come out. There are few results which link the TPM, transition probabilities, with first passage probabilities. Again, we have proofs for this, but I'm not including them. So PIIN, PIJN, here everything is II, here it's J, JJ. And there's another result that says that if I have sum of PIINs as infinity, then state is recurrent. If you have less than infinity, it is transient. Earlier we had said that if sigma FIIN is less than 1, it is recurrent. Equal to 1 means transient. So in this example, I'll be exploring the recurrence or transience. We have a Markov chain. State space has 4 states. Transition probability matrix is given by this. Here again, each row sum is 1. And this 1 here, this one means that state 4 will be an absorbing state. Because once it goes to 4, it does not come out. So it will be a recurrent state. It's not an irreducible Markov chain. Why? Because 4 does not communicate with any other state. 4 does not go to 0, 4 does not go to 1, 4 does not go to, 1, 2, 3, yes. And once it's here, it's always there. 3 does not go to 1, does not go to 2, it goes to itself and to 4. But 3 and 4 don't communicate because 4 is not going to 3. And here 1 goes to 2, 2 goes to 1, so they are communicating. So there are these 3 classes. 1, 2, 3 is separate and 4 is separate. So it is not an irreducible Markov chain. So what I have to do is here, I'll have to check recurrence of one of these 2 states, then this state and this state. So my exercise is increased because I'll have to do it 3 times. So first of all, we are considering third state. What is F331? F331, 3, this one. This is 1 by 4. F332, 1 means in 1 step. First return to 3 in 2 steps. First return. So 3 is going to 4, 4 is not going to 3, but I just split this as this. So because this is 0, second part, it becomes 0. Similarly, if I go to 3 steps, start from 3, end at 3, in between there is no 3. You can't take 3 in between. So P34, P44 is 1, I know, but P43 is 0. So again it is 0. So if we go on like this, 4 steps, 5 steps, they will all be 0. So we are left with only this one, this probability, non-zero probability. So this sum will have only one term, non-zero term, which is 1 by 4, less than 1. So state 3 is transient. So we have decided about state 3. It is a transient state. And when a state is transient, we don't talk of positive or non-null things or mean recurrence times. So we are finished with state 3. Then states 1 and 2. We just look at 1. They are communicating 1 and 2. So whatever happens for 1 will also be say true for state 2. Here F11 is half. F112, again you see start from 1, go to 1. In between you don't have 1. So these we have written from the TPM. So we have 1 by 2 square. Then 3 steps, P12, P22, it should be P21. This is wrong actually, typing mistake. It should be P21. So it's 1 by 2 whole cube. And when n is greater than or equal to 3, start from this P12, P22, n minus 2 steps, then P21. So n minus 2 plus 1 plus 1. That makes n steps. So it is half raised to power n. So when I take F11, we are getting a geometric series. And I'm getting F11 to be 1. So state 1 is a recurrent. And a recurrent state is also known as a persistent state. And this implies 2 is also recurrent or persistent because 1 and 2 are communicating. So that class is taken care of 1, 2. Now we are left. Okay, sorry. Because this is recurrent, so I have to see the mean recurrence time also. Mu11. N half raised to power n. This will be a combination of AP-GP series. So when solved, this gives me 2, which is finite. So state 1 is positive or non-null recurrent. And again, class properties hain ye. So state 2 will also be positive or non-null recurrent. So state 4, I said it's an absorbing state. And so it is recurrent. So we can find the mean recurrence time. Here, we are splitting this sum into 2 parts. N equal to 1 is separate. For n equal to 2 to infinity, I have all zeros. So P44, which we know is 1 from the TPM, which is finite. So state 4 is positive recurrent. So again, I will show you the R code for this. Okay. We have 4 states here. Na? So you see, for this, I have to install package Markov chain. There's a package Markov chain. So you have to install that. Then library, Markov chain. This is some other problem. This is ours. So P, this is my P, half, 0, 0, half, 0, 0, then 0, 0, 1 by 4, 3 by 4, and last one. Check sum across equal to 1. So it's 1 for all 4 rows. Then we are defining DTMC means discrete time Markov chain. You can give any name. You can just write X. So new Markov chain transition, M is capital here, equal to P because I am writing this TPM as capital P. States are 1, 2, 3, 4 in a vector. Name is DTMC. So when I do this, again it's showing me with the same transition. It says transition matrix, same thing it's showing. Then let me try plot. You see, on the right hand side, I had 1, 2 communicating. So 1 goes to 2, 2 goes to 1. These are the probabilities 0.5. वो थोड़ी mingling हो रही है. It's not too good a graph. And 3, 4 are not having any link with 1 and 2. But one side link is there, 3 to 4. So 3 goes to itself with probability 0.25. 4 goes to itself with probability 1. And 3 goes to 4 with probability 0.75. Now then we want to see recurrent states. Here S is again capital. So you see here. It says 1, 2, 4 are the recurrent states. And we saw there when we were making all those calculations that 1, 2, and 4 are the recurrent states. Then recurrent classes. There are 2 recurrent classes, 1, 2, and 4. 4 is separate from this class. So that's why it's showing 2 classes. Then transient states as capital of this. If I had written X here, then it will be X here, X, X everywhere. So transient state is 3, which is matching with our result. Transient class is just 3. Then we find the mean recurrence time. R is capital. It will not accept if you write R as small. So these are the mean recurrence times. This is for fourth state, 1. First state has 2, second state has 2. And we saw there that mu11 is 2, mu22 is 2, mu44 is 1. And it will not show mean recurrence time for 3. It's not showing the period because it says matrix is not irreducible. So that's why there is a warning here. So whatever we do there, if I spend half an hour on deciding about the recurrence or transience or finding mean recurrence, R does it in less than 5 minutes. Because if I type everything, I had it typed, so I didn't type again. So it may take you 5 to 10 minutes. So you can do, and the package is Markov chain. Now, what is a stationary distribution? For finding this, we have to solve pi equal to pi p. P is your TPM. This pi is a vector consisting of n components, or jitne bhi, if you are considering an example, Whatever is the number of states, you will have that many components in this vector. Each pi I is greater than or equal to 0. They are also probabilities actually. And sigma pi I will be 1. Please note that if your Markov chain is irreducible, positive recurrent, and aperiodic, then unique stationary distribution exists. If it is null recurrent, then no stationary distribution exists. If you have a reducible or periodic Markov chain, then infinite number of stationary distributions exist. So for existence of a unique stationary distribution, the Markov chain has to be irreducible. Irreducible means all states will communicate. Once a state is positive recurrent, all states will be positive recurrent. And if one state is aperiodic, aperiodic means period will be 1, then all will have period 1. In that case, we will have a unique stationary distribution. So these conditions actually should be in mind while deciding about how many stationary distributions are going to be there. So we are considering S as 1, 2, 3 with this transition probability matrix. We wish to determine pi 1, pi 2, pi 3 such that pi is equal to pi. Now let's check whether there is irreducibility or not. I have 1, 2, 3. 1 goes to 3. 3 goes to 1. So 1 and 3 communicate. 2 goes to 1. 1 is not going to 2. 2 goes to 1. 1 goes to 3. And 3 goes to 1. So via another state, it is having that. And one state 1 here, P11. This is coming out to be 0. In one step, this probability is 0. So this doesn't seem to be aperiodic. Because if one of the number is 0, we can't have period as 1. Here, no state is absorbing 2 to 2. No state is absorbing. So if we put in pi as pi 1, pi 2, pi 3 equal to this into P and multiply, I get this vector. So comparing both the sides, you have pi 1 as pi 2 plus pi 3 by 2, pi 2 as pi 3 by 2, pi 3 as pi 1. So if I add these three, because this is one of the conditions, and solve, I'll get pi 1 to be 2 by 5, pi 2 to be 1 by 5, and pi 3 to be 3 by 5. And we can see the sum is, sorry, there is some problem. No? It should be 1. Sorry, I think this is 2 by 5. This is again a typing mistake. Pi 3 is again 2 by 5. Because if I put 2 by 5 here, pi 2 will become 1 by 5. So this should be 2. Sum is not a 1 actually here. Then few more results are, if a state is recurrent, then if you take the limit as n goes to infinity, this means if n goes to infinity, nt is also large. This is t upon mu I, where t is period of state I. If t is 1, that is I is aperiodic, this t gets replaced by 1. When I is null recurrent, this will mean mu I is infinity. So this will become 0. Sorry, this should also be not tending. Now, there is a result and an example. If you have an irreducible and aperiodic Markov chain with capital N states, the TPM is doubly stochastic, then stationary probabilities are pi I equal to 1 over n for each I. This result helps you a lot when you have more than 3 or 4 number of states. And this question was also given in, not this one, I'll show you the next one. That was in, I think, UGC net question. So actually people think that there are so many states, how will we go about it? But it's very simple. Just check the irreducibility, aperiodicity, and doubly stochastic. So here, if you consider this TPM, you see all rows are adding up to 1. All columns are also adding up to 1. So it is a doubly stochastic matrix. It is an irreducible Markov chain. Each state can go to every other state. So they are all communicating. Aperiodic Markov chain means 1 goes to 1 in one step. So period will be GCD of 1, comma, so on. So it will be 1. For 2, again, this is positive. So it goes in one step. So period of the state will be 1. And when they are communicating, all of them will have same period, which is 1. And this is an aperiodic Markov chain. This we have already checked. So stationary probabilities exist, and this pi I, because there are 3 states, here I said 1 over n, it will be 1 by 3 for I equal to 1 to 3. I didn't solve any equations like I did in the previous example. I directly said that it is this. Sorry. Sorry, sir. Now again we consider a Markov chain which has 23 states. Now if I have to find pi 1, pi 2, pi 23, it will be a complex thing. So we can see the matrix, whether the matrix is doubly stochastic or not, whether irreducibility is there, whether aperiodicity is there, and I can directly say that my transition, my stationary probabilities are 1 by 23. Here we are given this. If I is from 2 to 22, then these probabilities are half. Moving forward, moving backward. Then P12 and P123 is again half. From 1, it's possible to go to second state and 23rd state. From 23rd again, it's possible to go to first state and the previous state, 22. Both of them are again half. So, now as we can show all the states, here I have written 1 to 2 half, 1 to 23 half. Then 2 to 1 half backward, 2 to 3 forward half. So like this you can go on writing the matrix. Here I had 23 ones, which is half, and 23, 22 is half. So you can see all rows are adding up to 1, and even columns are adding up to 1 here. This is a UGC net question actually. So it is a doubly stochastic matrix, and you can check the irreducibility also actually, and aperiodicity as well. So pi I will be 1 by 23 because there are 23 states. You can't solve it otherwise in 1 or 2 minutes. Next thing that I want to take up is a one-dimensional random walk. Actually, a random walk is also a stochastic process. It's compared to the walk of a drunkard who doesn't know where he's going, moving forward, backward, to the left, right, like that. So there are 3 random walks. Okay, just a minute. I'll show you how to find stationary probabilities in R. Okay. You see here, install the package EXPM. This is stationary probabilities. So EXPM, then library. You see here, what we are doing, we are raising P to the power 100. It's now, this is exponentiation sign. So if I do this, I'm getting this result. And then if I do this, I'm getting same thing. Okay? If I further raise it to 1000, I'll get again the same thing. So what you have to do, you just raise P to a higher power to get the stationary probabilities. It's better here when you raise it to power 1000. So 0.5, half, 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 0, 1, 1, 1. So this is what you are getting. And another thing is how to draw this one, which I had plotted last time. This is known as transition probability diagram. Here we have to, actually this is not our example, I've just picked up from somewhere. So library, I graph. Then there is this matrix, TMD. So this is the matrix. 3 states are cheerful, so-so, gloomy. These are the moods of a person on a day, and what will be his mood on the next day. Maybe I'm cheerful today, I may be gloomy tomorrow, I may be so-so tomorrow, like that. I may be gloomy today, I may be cheerful tomorrow, and so on. Then See here. So this is my transition diagram. Cheerful to cheerful. First state is cheerful. So that is 0.7. So cheerful to cheerful, 0.7. Then so-so to so-so. This is 0.3. So this one. And gloomy to gloomy. Gloomy is third one. So 0.4. Actually, yahan nahi aa rahi hai. It's not showing. If I zoom it more, though, it's this. Gloomy. And here, 0.2 is the probability of being cheerful today, gloomy tomorrow. And 0.1 is gloomy to cheerful. Similarly, these are directed arrows. This is so-so to gloomy. This is gloomy to so-so. Then so-so to cheerful and cheerful to so-so. Okay. So this is how we can write this program. And then actually I didn't follow why he is giving two commands. Here colors are not there, but everything else is there. Main is mood, so it is depicting the moods. Okay. In one-dimensional random walk, every transition, the particle or an individual moves one step to the right with probability P and one step to the left with probability Q. Sum of these two is 1. Here all states communicate with each other. If you start from the origin, 0, 0 to 1, then 0 to -1. The number line is also on the left side with negative numbers. Then -1 to 0 or -1 to -2. For state 0, P001 is 0. It will not stay in 0. It will either move to the right or to the left. दो steps होंगे, it will be positive. 0 to 1, 1 to 0. Then 0 to 1, 1 to 2, 2 to 1, 1 to 0. 4 steps. These probabilities are positive, but if you take odd number of steps, those probabilities will be 0. Same return possible nahi. So period of state 0 is GCD of 2, 4, 6, which is 2. And definition says that we take GCD of those numbers for which probabilities are positive. It can be shown that for both P and Q to be half, state 0 is a recurrent state, and since all states are communicating, they will all be recurrent. If P is greater than Q, that means probability of moving to the right is more than moving to the left, then there is a positive probability that particle initially at 0 origin will drift to infinity, because it will move to the right more often. If P is less than Q, then there is positive probability that particle initially at 0 will drift to minus infinity. Because here, probability of moving towards left is more. So there are chances that it can go to minus infinity. Then what is a two-dimensional random walk? Here, particle moves one step to the right, left, upwards or downward. Now you are in two-dimensional situation. So probabilities are P1, P2, P3 and P4, where sum of all the four probabilities is 1. Here again, all states will communicate with each other. Because if you leave one state, go to another state, in any direction, it will be possible to come back. So that's why communication is there. And same argument that odd number of steps probabilities will be 0, even number of step probabilities will be positive. Because once you leave 0, या तो आप 2 steps में वापस आएंगे, or you will come back in 4 steps or 6 steps and so on. So again period will be 2. And for all of these to be same, it can be shown that all states are recurrent. Actually, if they are not same, proof is very involved. And generally books take up the case when they are all equal. In three-dimensional, there are 6 sides now. Right, left, upwards, downwards, and 2 sides in the third direction. These are the probabilities, and sum of these has to be 1. Same argument, communicate with each other. Return to any state is possible only in an even number of steps. So period of each state is 2. And if pi is 1 over 6, that means all of them are same. Because sum has to be 1, so 1 by 6. Then it can be shown that all the states are transient. This is the difference between 1, 2 and 3-dimensional random walk. In 1 and 2, all states were recurrent. But in 3, all states are transient. Now this is again a very interesting problem which is studied in stochastic processes. Consider a gambler who on each successive game or trial wins 1 unit or loses 1 unit, independent of the past, with probabilities P and Q respectively. So P is the probability of winning, Q is the probability of losing. His objective is to reach a total fortune of capital N units without first getting ruined or running out of money. Capital N units is the total money in the game. Suppose total money in the game is 200. I have 100. My adversary has 100. So 200 is the total fortune. Either I will lose all my money or I will get something from my adversary, and he will want to reach total N units. So if he succeeds, then he wins the game and he stops playing after winning or getting ruined, whichever happens first. If his capital is reduced to 0, he can't play. And if his adversary's capital is reduced to 0, then there is no game. Now, the probability that the gambler wins when he starts with I units, I is between 0, positive, and less than n. क्योंकि अगर full उसी के पास है, then adversary will have nothing. So it will be less than capital N. And PI, suppose it is the probability that gambler wins when he starts playing with I. So this is the formula that is derived after a few calculations. This comes out to be this. If P is not equal to Q, then this is the formula. I is the starting capital. Capital N is the total capital in the play. And if both are half, then it is I upon capital N. So if you know the value of Q, P, I, and N, you can find this probability. And this is the probability of winning. Then probability of his ruin. It is 1 minus that expression on the last slide. So we get this. So if you have to find the probability that gambler will be ruined, then this is the formula. There is a proof for this also, but again, as I said, I'm just giving you a brief insight. So this is an example for gambler's ruin problem. Suppose that the starting money is 2 units and probability of winning is 0.6. First is, what is the probability that he obtains a fortune of n equal to 4 without going broke? So I is 2, n is 4, q is 0.4. So q upon p will be 2 by 3, and this is the required probability because I'm saying winning. This is the probability of winning. If we want to find the probability of losing or ruin, it will be 0.31, 1 minus 0.69. We can also find expected duration of the game and all that. That is also possible. See, as I said, there are many types of stochastic processes. We had random walks, then we considered gambler's ruin problem as an example. Now I'm coming to Poisson process. Let me see how much I'm able to cover. This Poisson process, here time space is continuous, state space is discrete. And it is one of the most widely used counting process. Why we call it a counting process? Because we count the number of occurrences. So usually used in scenarios where we are counting the occurrences which happen at a certain rate but completely at random. So where will they occur randomly in space and time? Accidents, nobody is sure of meeting with an accident. Where the accident will happen and when will it happen, nobody knows. When will death happen and where will it happen, nobody knows. So it is completely at random. And if from historical data, it's known that earthquakes occur in a certain area with a rate of 2 per month. Other than this information, timings seem to be completely random. So Poisson process is a good model for earthquakes. And it is also used for modeling the number of car accidents at a site or in an area, location of users in a wireless network, requests for individual documents on a web server, outbreak of wars, incoming telephone calls, arrival of customers for service at a counter. Actually, all those examples which hold for Poisson distribution, they hold for Poisson process. Only difference is in Poisson difference distribution, you consider only one unit of time. Here, we are considering an interval of duration small t. What happened between 24 from 8 a.m. to 8 p.m. So we are giving an interval of 12 hours or 24 hours or 36 hours like that. So NT is the number of occurrences of a random event in an interval of duration t. Notation is NT equal to a small n is PNT, where n is 0, 1 to so on. And sum of these probabilities has to be 1. There we used to write capital N equal to small n. Here n is a function of time, duration. Now let lambda be fixed. It has to be positive. The counting process NT, where t belongs to 0 to infinity, it's a continuous time space, is called a Poisson process with rate lambda, or sometimes it's also known as intensity if the following conditions hold. N of 0 is 0. The number of occurrences in an interval of duration 0 will be 0. That makes sense. It has independent increments. But if you are in one interval 0 to t1, what happens there does not affect what happens in t1 to t2. Then it depends only on the length and not on the location of the interval. Number of arrivals in any interval of length t follows Poisson. Now parameter changes. In Poisson distribution, you have lambda. Here we have lambda t. So under the mentioned conditions, this P and T is equal to this. This is that Poisson probability with now parameter lambda replaced by lambda t. We proved this also. Why do we get P and T equal to this? There is a 2 to 3 pages proof for showing this. Then what is the distribution of the inter-arrival times? Inter-arrival times means the times between successive occurrences of events. One birth occurs at 9 a.m. The second occurs at 12, so 3 hours gap. That is an inter-arrival time. Then third birth, may occur at 4 p.m. So that is your time between 12 to 4 will be inter-arrival time. So if we have a Poisson process with rate lambda, then the inter-arrival times are independent and all these TIs, they follow exponential with parameter lambda for I equal to 1 to 3. So this means that inter-arrival times are IID random variables. They're independent as well as identically distributed as exponential. And this is also a very important result. So this example is saying that we are modeling the number of customers at a grocery store by a Poisson process with lambda equal to 10 customers per hour. We want to find the probabilities that there are 2 customers between 10 and 10:20. Then second is to find the probability that there are 3 customers between 10 and 10:20 and 7 customers between 10:20 and 11. So here there is a split. So lambda is given to be 10, and between 10 to 10:20 the time length is 20 minutes, which is 1/3 hours. So if n 1/3 is the number of arrivals in that interval, it means this follows Poisson with 10/3. Lambda is 10, t is 1/3, so 10/3. So I am interested in finding that number of arrivals is equal to 2. So equal to, this is the parameter, raised to power 2 over 2 factorial, e raised to power minus 10/3, and this is approximately equal to 0.2. For the second case, we have now 2 non-overlapping intervals. I1 10 to 10:20, I2 10:20 to 11. Actually, here I am not including it, here it's closed. So we want this probability 3 arrivals in I1 and 7 in I2. Independence means I can take the product of the 2 probabilities. So 3 in I1, 7 in I2. Lengths of the intervals are, first is 1/3, again 20 minutes. Here 40 minutes, so 2/3. So we have lambda t1 as 10/3 and lambda t2 as 20/3. So probability is given by the product of the 2 probabilities. In one it's 10/3. In the second it is 20/3. Here I have 7. Here I have 3. So this is approximately equal to 0.0325. Then this is another example of stochastic process, branching process. You must have, you are familiar with family trees and all that. So there is one individual at the top, then there are branches like that. So branching, that's why it's called a branching process. This models population growth and is used in fields like biology, epidemiology, and nuclear chain reactions. Features are that each individual starts a family of descendants. All these families have the same stochastic properties and they do not interact with one another. So suppose X naught is the size of the starting population and it is assumed to be 1. Pk is the probability of giving birth to exactly k new offsprings, and sum of these probabilities is 1. Xn is the size of nth generation. Nth generation means they are descendants of the individuals in the n minus first generation. Process is Markovian in nature because size of nth generation depends upon the size of the n minus first, and so on. Expected size of nth generation is, we assume initial population size to be 1, expected population size to be m, and variance of x1 to be, these are for the first generation. ये initial है, where m and sigma they are existing and are finite. Then expected size of the nth generation is m raised to power n. And variance has this formula. First is for m not equal to 1, and then sigma square for m equal to 1. So if I know, suppose I know m, I know sigma square. I want to find the expected size of 10th generation. I can just replace by n by 10. In branching processes, probability of extinction is also an important concept. Suppose M is the mean number of direct descendants of a single individual. ये वही first generation का वो है. If this M is less than or equal to 1, then probability that the process will terminate before nth generation tends to 1. So probability of extinction tends to 1 if M is less than or equal to 1. Directly we say that probability of termination or extinction is 1. If M is greater than 1 and PS is the probability generating function, then we solve this equation S equal to P of S, find the root S which is less than 1, which will be unique, and this unique root is the limit of the probability that the process terminates after a finite number of generations. So everything is dependent upon value of M. Suppose I have this setup. P naught is probability of producing no offspring. It's 1 by 12. 1 offspring, 2 by 3. 2 offsprings, 1 by 4. M here comes out to be 7 by 6, which is greater than 1. So we solve this equation, S equal to PS. PS is here, S is raised to power 0, 1 by 12 plus 2 by 3 S plus S square by 4. When you will solve this equation, you will get S1 and 1 by 3. Roots will be these two, and 1 by 3 is less than 1. So probability of extinction is 1 by 3. And if it had come out to be 5 by 6, which is less than 1 or equal to 1, then I'll straight away say the probability of extinction is 1. Actually, I am trying to cover a lot, but just this is a brief introduction now. Then renewal process counts random events over time, where the time between events, these are the interrival times, they are independent and identically distribution. It's a counting process again. You count the number of renewals. Renewals here means whenever a new occurrence happens. You have bulbs, you replace a bulb, that's a renewal. A person is replaced in a job, that is a renewal. So a counting process where time until the first event occurs has a certain distribution. Interrival times are independent and drawn from same thing. They are used in many areas: physics, biology, engineering, reliability, queuing, and finance. And in reliability modeling, this process models the failure process of a system, which is replaced with a new one after failure or is as good as new after repair. Maybe a component fails. You either replace it fully or you repair it and then put it back. So those are renewals. Then birth and death process, they are special type of continuous time Markov chains. States are 0, 1, 2. If j is not equal to I minus 1, this probability is 0. And j is not equal to I plus 1, again it is 0. It's known as a birth and death process. CTMC means continuous time Markov chain. And transitions can happen only from I to I plus 1 and I minus 1. This is small I. So every transition either causes an increase in the state by 1 or a decrease in the state by 1. Birth hai, so it will increase by 1, and death means state decreases by 1. Stationary process is a process in which statistical properties do not change over time. Distribution of xt is same as x of t plus h for all h positive. First two moments of the process are finite and constant. And if you consider the autocovariance function, it will be a function of the mod of t minus s. Then Brownian motion is another continuous time, continuous state. Origin is in physics for motion of small particles immersed in a liquid, is a mean zero continuous process with independent Gaussian increments. Gaussian means normal. Increments are independent and they follow normal distribution. This is at the basis of the mathematical modeling of financial markets and can be used to model the fluctuations of stock prices. So it's a Brownian motion or a Wiener process. Sigma square is the diffusion coefficient. W0 is 0. Wt has independent stationary increments. And for every t, Wt is normally distributed with 0 mean and variance, sigma square t. So this normally means Gaussian. So these are the references. Last book deals with introduction to stochastic processes with R. And mainly people follow Medhi or Ross. So thanks for a patient hearing. So any questions? Shall I stop presenting or keep it?
Yes, ma'am, you can stop presenting. Anyone is having questions?
I tried to cover a lot.
Yeah, sure. You definitely, ma'am.
Very good presentation, ma'am. Thank you so much.
Thank you. Thank you. I could not include the details because in 2 hours I
Yes,
could
ma'am.
do only this. I think
Okay.
एक और है. Just a minute. मुझे ना R में कुछ और दिख अब तो ये कह रहा है डिसमिस कर रहा है. I just want to comment.
Yes.
If you, like we were looking at stationary probabilities, and I was raising P to power 100, 500, 1000 like that.
Okay.
There's another command, steady states,
Okay.
with the states as capital. I think I'll write in the chat box. I think I didn't show this. So for finding steady states means you are finding that stationary probabilities. You can do this also.
Okay, ma'am.
So I hope I was able to make myself understandable.
Definitely, ma'am. Ma'am, there is one question
Just
that
a question.
yeah,
Yes.
between the arrival base follows exponential, shall we take the different distribution in Poisson process?
Just a minute. Between the rival always follows exponential. What type of distribution? Poisson process follows Poisson distribution. When we are talking of Poisson process, that means capital NT, which is the number of occurrences in an interval of duration t, will follow Poisson distribution with parameter lambda times t. The rate into the length of the interval. You can't take different distribution. It's for a Poisson process only that inter-arrival times follow exponential. You can't change that.
Anyone else? Or can we proceed? Okay, Rahul. I think we can proceed.
Yes, sir.
My throat was not favoring me. I was fine till 5 o'clock. I don't know what happened after that.
So
I was completely fine before 5.
it's okay, ma'am.
Actually, weather is like that. Everyone is having sore throat.
Yeah, in the north it is changing drastically
Yeah.
the whole day, so that's the problem.
Yes.
I understand.
Yes. So thank you, Dr. Shikhar.
Thank you.
Thanks a lot for your invitation.
Thank you, ma'am. Rahul, you can proceed now.
Yes, sir. So thank you, Professor Jain, for such an insightful and engaging session on stochastic processes. Your deep expertise and clear explanations have provided us with valuable knowledge and practical skills that will greatly benefit our academic and research work in stochastic processes. We truly appreciate the time and the effort that you have dedicated to give this session, and we look forward to applying what we have learned today in our future works. So thank you once again, ma'am, for being with us and sharing your expertise.
Thank you, Mr. Samuel. And thank you, Dr. Shikhar, for inviting.
Please, I will request to our HOD, Professor Vinam, for the validatory speech. Please.
Good evening. My audio is clear?
Yes, sir.
Okay. Thank you so much, madam. It was really a wonderful presentation.
Thank you, sir.
I never sit for such a long session on the statistics generally. I'm a computer science person. Generally, I don't sit, but this was making me more interesting even when I'm listening. You made it more simple and more clear, and it was very clear for me as well. It was very interesting, and thank you so much taking your time, spending your valuable time for giving your knowledge to all our people who are interested, and they joined this especially for learning only. This was FDP was majorly we planned it for conducting purpose, that so that knowledge is from an expertise are shared with the total. I think your 40 plus of your experience is clearly shown on today's that when you did the presentation at all and your subject expertise at all. Thank you so much, ma'am. And from my side, I would like to congratulate Dr. Shikhar and his team for arranging, including the few of the students who supported this, faculty members who have made this continuous every day after the office hours, and then people sitting and learning from an expert. It was really a great pleasure in learning and listening to these expertise at all. I was not able to attend all the days at all, only 3 days I think I was able to log in and then see some of these presentation I could work on. Because of several days it was a rain, or I was stuck up, held up with some other work. But still, whichever I attended, I could grasp that kind of expertise whom he has gathered, maybe requested, and then found them at all, and then getting them is not easy at these days at all. But since it was an online, I think all of them were very happy, and they shared very well, from senior lecturer to a publisher, the 60 research plus papers who have come onto this at all, and senior expertise who are also had sharing their experiences with these kind. It definitely help the participant as well as for our students who are also a part of this. It is very much indeed experiential learning for them. That's the reason exactly this made a very wonderful experience for all of us, and the knowledge sharing sessions for all of us. Hope from all of us, as an organizing team, I would like to thank all the resource people who came, plus additionally to all the students who helped us, management who gave us the permission to conduct these things, as well as the Shikhar and his team to make it a wonderful experience. I think Gobinath sir is also here, and he also took an initiative to ensure that all the arrangements have been done at all. Once again, thank you everyone. Thank you so much.
Thank you, Professor Vinay, for your
Thank you.
kind words.
Yes, thank you so much, sir, for
Thank you,
attending
sir.
this all. And with this, we come to an end of this 7-day national level workshop. Before concluding, I would like to give a few instructions regarding the same. The feedback form for today's workshop has been shared in the chat box. Kindly fill today's feedback form. And all the 7-day recordings and the PPTs, the materials, the R codes, whatever has been discussed by the resource persons will be shared to all of y'all through the email as well as WhatsApp groups through a Google Drive tomorrow. So please check your emails as well as WhatsApp group. We will be sharing it by tomorrow. And the certificates for a certificate for individuals for attending the 7-day workshop will be sent to you all through your emails within a week. If after a week, if you all haven't received, you can always get back to us. You can ask through the mail or WhatsApp group. So we'll be always available to take your queries through WhatsApp or email. So thank you once again to all the participants who have tuned in for all 7 days and for making this national level workshop on advanced statistical techniques a great success. Thank you once again and have a great night.
So shall I leave, Dr. Shikhar?
Yeah, ma'am. Sure, ma'am. We can leave.
Okay, thank you and congratulations to the whole team.
Thank you, ma'am.
Good work, Shikhar sir. It was wonderful. Many
Thank you so
feedback
much, sir.
also which came. I think I could go through them at all, and it was really they had a good experience and really good resource people who had shared their knowledge as well.
Thank you so much, sir. Thank you for your support, sir.
Oh, thank you.